All right, let's get started with lecture 4. So we're going to continue our discussion of the Schrodinger equation and talk about something called the stationary state. So before starting the new discussions, let's just see where we are, what are the things we've done. So thinking about the book by Randy Harris, to give you some notion of like where to read to review the material we've covered. So we started talking about the photoelectric effect, right? So review of the things we've done through the entire course. So first we talked about the photoelectric effect. And that's discussed in section 3.2. Of the book. So the upshot was that to explain this experiment where you shoot electrons on a piece where you shoot light on a piece of metal and it emits electrons, and you measure the kinetic energy of these individual electrons. To explain it, we had to treat light as kind of particles with energy given by h times the frequency. Which is a different, really, point of view from treating light as an electromagnetic wave. That doesn't work. That doesn't explain this experiment. And then we talked about matter, things like electrons exhibiting kind of similar wave-like behavior. So there was the double slit experiment, where you send electrons through two holes, they hit a screen, they're detected as individual particles, but if you keep repeating this, after a while, this pattern of fringes, like brighter regions where more particles hit and darker regions where fewer electrons hit, appear. So basically, the way to explain it was that, well, there's some probability distribution for this, and you have a higher probability for brighter regions. So a natural way to describe these electrons is to think about a quantity kind of analogous to the electric field, which when you square it, you get the probability, which is kind of analogous to the intensity of light, right? The more probability, the brighter that region becomes. So this was something that we discussed, or is discussed in the book in section 4.1. Before doing that, there was this discussion where we talked a little bit about the de Broglie results, like what would be the wave-like characteristics of particles if we want to make an analogy with light that we understand has this property, has some relationship between momentum and energy. So we had the de Broglie relationships. So a good place to read about them is in section 4.2, properties of matter waves, or we write it as section is called properties of the matter wave. So the de Broglie wavelength, for example, is discussed there. And then in general, we started introducing the wave function and talking about the probabilistic interpretation. So psi of x and t, for example, in one dimension, and then the interpretation is that psi of x and t absolute value squared dx is the probability of finding the particle in this interval. So this is to some extent discussed in section 4.2. Also, section 4.3 talks about like the free particle Schrodinger equation. So yeah, so talking about matter waves, again, we make this analogy with waves and try to make use of the de Broglie relationships, and found that free particles satisfy, that for free particles that the wave function satisfies this. Basically no potential, nothing. So there we kind of expect plane waves constructed as solutions that satisfy the de Broglie relationships, and the energy is just the kinetic energy, p squared over 2m. So you can read about that. It's helpful to review these concepts in section 4.3 of the book. And then the last thing we did was introduce the more general Schrodinger equation where you have a potential. So then the idea was that this operator that acts on the wave function, this minus h bar squared over 2m times the second derivative with respect to x, is doing is effectively like the kinetic energy. So to write the more general equation, it makes sense to add the potential to this. So the last thing we discussed was the Schrodinger equation. So let me put some items here because one of them took 2 lines. So let's say 1, 2, 3, 4, 5. The more general case, the time derivative of this wave function is going to be minus h bar squared over 2m. The second derivative with respect to position plus v of x acting on the wave function. So this, you can distribute it through. So this is interpreted as, this thing times the second derivative, basically that quantity plus v of x psi of x and t. So now the framework we have is to kind of the model that we've come up with. The model that we've come up with describes the particle by something known as the wave function. It's some mathematical object which satisfies this equation. So it evolves, right? It gives you the rate of change as a function of time in terms of like some spatial derivatives and the potential. So it evolves with that differential equation in time. So that's the fundamental equation that governs the behavior of this mathematical quantity. This is really the analog of, let's say, Newton's second law, F equal ma, right? The forces are kind of encoded in this potential, mass is there, and now it tells you something about how this wave function changes. And in terms of the interpretation, we know that wave function squared tells you about the probability of finding the particle somewhere. Another thing we've spent some time on so far is basically calculating kind of averages and expectation values and probabilities with the wave function, right? So this was, for example, the probability of being in some tiny interval. So to be in a finite interval, we talked about integrating that probability density to find the probability of being like in some interval between A and B. We also talked about finding the average of position, right, where we multiplied the probability distribution by x and performed that integral to find the quantum average. So a good place to read about about that is in section 5.8. So quantum expectation values. Basically, the only thing we discuss is the average of x's integral from minus infinity to plus infinity of x psi of x, and it could depend on time if it does. That thing squared, so then this average becomes a time-dependent thing, and then you integrate over x. All right. So I wanted to take a second and also tell you a little bit about Wolfram Alpha. So this is a free kind of web-based application that we can use to do integrals and things like that for the homework. As it said in homework 2, you don't need to do the integrals by hand. And in quantum mechanics, we need to do a lot of integrals. So just to see, like, you go to wolframalpha.com, and then here, calculus and analysis. And then if we're interested in integrals, there are like indefinite integrals and finite integrals. So let's just click on this. So this is the integral of x squared sine cubed of x, and it's an indefinite integral, and you just calculate that. So if you want to change something, you know, and insert parameters, let's say, I don't know, sine squared or sine to the fourth of x over a. It's going to be very complicated if it manages to do it, but let's see if it does it. Yeah, it finds some, again, answer that depends on a and x. So that's an indefinite integral. You can even use definite integrals, just put the range. So integral sine x from x0 to pi, okay, it calculates it. The answer is 2. You know, if you want to do sine squared of, I don't know, f is some number times x from 0 to b, some other number. Again, it's going to calculate that integral, and it gives you an answer as a function of f and b, for example. All right, so it's a very useful tool. Once you reduce the problem to some integral, you can just plug it in there. All right, so let's now keep going with the Schrodinger equation. So what I want to discuss today is so-called stationary states and obtaining the time-independent Schrodinger equation, which tells us about stationary states from the time-dependent Schrodinger equation. So we said let's do this kind of quantum classical analog, right? Classical quantum. And in classical physics, like if you think about configuration, so if you think about one particle, right, let's say in one dimension, to know everything about that particle in one dimension, you just need to know x and p, right? If you know where it is and what the momentum is, which means how fast it's moving instantaneously at that moment, and then if you know all the forces acting on it, you can predict the fate of that particle. In quantum mechanics, what we know is at some point in time, for all positions, we know psi of x and t. So at any moment in time, the particle, we can't say, oh, it's in that point or this other point. If you measure it, you can find it all over the place. But there's this mathematical object whose square tells you, whose absolute value squared tells you about the probability of finding the particle in different places. And then, so if you think about dynamics, how things change, well, what is the dynamics here? So we have x or f, we have a bunch of forces, right? The net force is mass times the acceleration. So Newton's law kind of tells us about the future behavior of this particle. In quantum mechanics, the dynamics is governed by the Schrodinger equation, the differential equation we just discussed, that gives us the time derivative of this wave function. As a function of its spatial derivatives. Right, so if at some snapshot in time you know what that wave function is, maybe it looks like, I don't know, it looks like something like this. And then you know the potential that the particle is experiencing. So let's say that's psi of x and t equals 0, for example. And then the particle is experiencing some potential. I don't know, let's say there's something like this, like a v of x here. In this axis is x, I'm plotting two different things, the wave function and the potential. So somehow, you see, a little bit later, if you have a clock that ticks, like you add a dt, a tiny amount of time, to the wave function, right? That's a snapshot at t equals 0. This equation, well, you know this, right? You know the wave function at that point. You fix the time, you take the derivative with respect to position, you take the second derivative, so it's something that has to do with the curvature of this wave function at that instant, at that point in time, and then you have the potential, it multiplies the wave function. And then this becomes, on this side, at that point in time, you're getting some other function of x. So you multiply that by dt by this infinitesimal time, add it to this wave function, and that tells you how the wave function has changed a little bit later, right? So it's a first-order differential equation in time, and if you know the initial wave function, it can give you the final wave function. And the things that determine how it's changing is like how curved it is, right? So the curvature of the wave function is related to the kinetic energy. So the more curvature you have, the more you change. Also the potential kind of tells you again about how it's changing. It's kind of the derivative of the potential is the force, so it makes sense. Like if you have a potential with a well here, somehow you would expect maybe the particle wants to go to the bottom of the well or be confined in that well. And basically, like the effect is generally some kind of spreading out. So as time goes on, the particle may be found in more places as affected by the potential. Okay, so then you can ask, given these two very different models, these two frameworks, in classical mechanics we have the notion of a particle in equilibrium, right? A particle that's just sitting somewhere. It's not moving, and that's like the net forces maybe are 0. If it's a rigid body, maybe the total torque is 0 as well. But just, in the simplest case, a particle that's in equilibrium, well, we know that like moving with constant velocity is not different from just sitting somewhere. There's some inertial reference frame that you're stationary. So the question is like, what is the analog of this? So this is like basically like the second derivative is 0, right? There's no acceleration. That's how you would describe equilibrium in classical physics. And in quantum mechanics, basically to talk about some state, some wave function that's stationary, means that the probability density, this guy, is not changing as a function of time. So that's the notion of equilibrium in quantum physics. And it turns out these correspond to separable solutions. So this is something that, I'm just stating now, and we'll see how it works out. So basically, psi of x and t is going to be a function of time times a function of position. So the notation is a little bit unfortunate here. So basically, like this is typically written as like capital psi, and then we write it as like a curly small psi of x times another function, let's say phi of t. So let me see how I can make that notation clear. Yeah, so basically for the capital one, I put these horizontal lines. So I write it always as this. I try to write it bigger. And this is like a small size. The same Greek letter. Yeah. When you see it in print, it's easy to distinguish, but when you write it by hand, it can become a little bit confusing. But basically, the idea is that if that's the case, if you find the solution to the time-dependent Schrodinger equation, this guy, that's separable, that looks like this, then the probability distribution is guaranteed to be time-independent, as we will see. Okay, so here's the derivation that I want to discuss, and this is this you can find in section 5.2 of the book. So section 5.2, stationary states. Okay, so consider a solution of the Schrodinger equation that can be written as a product of a spatial part and a temporal part. And this technique is called separation of variables. So consider solution to time-dependent Schrodinger equation. So we write the equation again. And we're saying we're separating the variables, so we're looking for the type of solutions that can be written as a product of something that only depends on x and something that depends only on t. All right, so how can we find these solutions? Well, let's see. There are these derivatives, like the first derivative with respect to time and the second derivative with respect to position. So let's write those. So what is this guy here? Well, the only time dependence is in phi, right? So as far as time is concerned, that psi of x is a constant. It doesn't depend on time, so I can factor it out. And then here, now this is just a function of time, so I just take the derivative with respect to time of phi of t. Okay, so that's easy. Similarly for this guy, the second derivative with respect to position, now I'm in this function of position and time, it's like I'm fixing time, I just set in it to be some number, and I just find the derivative with respect to position. So now this phi of t is a constant. It doesn't depend on x as far as I'm interested in that derivative. So I can factor that out, phi of t, and then I find the second derivative with respect to x of psi of x. This notation, why I write this as d and that as kind of a curly d, is because these just depend on one variable. So when I take the derivative with that one variable, there's no other thing that I'm keeping constant. So it's just a notation. In this case, this is a function of x and t, so the derivative with respect to t really means I fix x. I treat it as a constant and then find how much is changing for fixed x if I change the time a little bit. Okay, so now these, right, I can insert into my original equation. So let's see. So I have IH bar psi x ddt of phi t is equal to minus h bar squared over 2m. Now I have phi t, second derivative with respect to x of psi x, right? And then plus v of x, just insert that product, psi of x, phi of t. Okay, so nothing special so far. But then I can take this equation and divide both sides by psi of x and t, or by the product of psi of x, phi of t. And you'll see in a second why that's a very useful step. That's kind of a standard technique in actually solving differential equations with separation of variables. So what I find is, well, IH bar psi of x divided by psi of x phi of t gives me 1 over phi of t, right? Because psi of x cancels out in the numerator and denominator, so I find 1 over phi of t. Derivative with respect to time of phi of t. That's now equal to minus h bar squared over 2m. Phi of t divided by phi of t times psi of x is 1 over psi of x. Right, again the phi of t cancels out. Second derivative with respect to x of psi of x. And then here, this just goes away, so I have v of x. So now we see the power of this technique, because here I have a function of time and here I have a function of x, of position. But for every time and every x, for every t and every x, they're the same, they're equal. So how can that be? I mean, if you have something that somehow changes as a function of time, right? So let's say this is some function of time that's somehow changing. Well, it must be equal. So let's say it's equal to that for every x, right? Let's just take one particular x, so that's a number. So it's going to be equal to that number here, and it's going to be equal to that number there. So then this can only be a constant. It cannot depend on time, because then this is equal to that. And similarly, this side must be a constant. So the magic of separation of variables is that we somehow start with one equation and we get two equations. So the only way this can be satisfied, we can have a function of time that for all times is equal to a function of x for all x's, is that this is a constant that doesn't depend on time. constant, and this guy is the same constant. All right. So now we're in business. And this is a really simple, like the first one is a simple differential equation. So let me just write it again. I can write d dt of phi of t. Let's multiply both sides by minus I. So minus I times I is 1. Kills is on this side. Let's divide by h bar. And we multiply by phi of t. And I have a c here. Okay, so I have the derivative of a function of time with respect to time is something times that function of time. So the solution to this is going to be the exponential, right? Because we know that the derivative of the exponential function is the exponential function. So this is e to the minus, again, ic over h bar, that's coefficient there, times t. Right? So we already see that because we found the solution of this form, the probability distribution is guaranteed to be fixed, because now psi of x and t is some psi of x that we haven't talked about yet, times e to the minus I c over h bar, some number times t. Okay, so what is the probability distribution? Is absolute value of this squared, which is psi of x and t times its complex conjugate, right? So it's psi x e to the minus I c t over h bar times psi x. Let's do that psi star because this thing could be complex itself, times e to the plus I, right? To take the complex conjugate, I just change the I to minus I. And then the product of these two things is 1, right? Because e to the minus ict over h bar, e to the ict over h bar is e to the sum of the exponents. That's e to the 0, and that's 1. Right? 1 is the inverse of the other. So this just becomes psi of x, absolute value squared, the time dependent, out the window. There is no time dependent for solutions of this form. So if you have a separable solution, it kind of guarantees a stationary, time independent probability distribution, as we discussed. And it turns out, so as we'll see, like these psi x's that appear are quite important. These describe like stationary states of atoms and molecules. So there's going to be, for example, some set of psi x's that are allowed for, let's say, hydrogen atom. And then there are some quantized fixed energies associated with those. And then this has real experimental consequences. For example, if you look at the spectrum of light emitted by a hydrogen atom, you're going to see only certain frequencies that are commensurate with the difference between the energies of these stationary states. So we're coming to all of that, but this is quite significant. And basically this equation now, here, the equation for psi of x, is an extremely important equation in quantum mechanics. It's called the time-independent Schrodinger equation. And it basically describes what are the allowed stationary states. So let's write that. So basically I can take this equation now and multiply both sides by psi of x, and I write time independent Schrodinger equation, which is basically, so from here, this psi of x disappears, so I have minus h bar squared over 2m. Second derivative with respect to x times psi of x plus v of x psi of x is that constant times psi of x. So remember what the original equation was? It was minus IH bar, derivative with respect to time of psi x and t is minus h bar squared over 2m, second derivative with respect to position, plus v of x. This whole thing acting on psi of x and t. So it's really helpful to treat this thing as an operator that acts on the wave function. And it's really something that corresponds to the energy of the system, right? This, we argued, was giving us the kinetic energy, for example, when acting on a free particle plane wave function. And this is the potential energy. So this whole thing we can call, let's say, h of x. It's an operator. It has a second derivative plus a function of position acting on something. So this equation, if I want to write it in a concise way, I can put a hat to specify that this is not just a function, it's an operator. Oops, there's no minus here, sorry. No minus. Right, so there's no minus in the Schrodinger equation. So that's psi of x and t is h of x, this operator times psi of x and t. And we're saying the stationary solutions are given by, say it's the same operator, right? So it's basically h of x acting on psi of x. Now there is no time dependence in psi of x. And the operator has no time dependence, let's say. So we're thinking about like constant forces, like a potential that doesn't change as a function of time, is some number times psi of x. So psi of x, this time independent function, is really an eigenvalue, is an eigenfunction of energy, right? You have an operator associated with the energy of the particle acting on this, and it's giving us a number times the wave function. So this number we can identify as the energy of the stationary state psi of x. So let's call that E. And this is the time independent So it turns out, for example, for a given potential, you can have only a certain number of allowed energies, because you must find the stationary state wave function that satisfies this equation, and that can only happen for some particular numbers, known as the eigenvalues of this operator. So this explains a lot of like atomic spectroscopy, for example. All right, so to recap, we just said that basically solutions to the time-dependent Schrodinger equation, which give a probability distribution that's time-independent, and those are really the equilibrium states of a quantum system, satisfy this new equation. So basically here in the time-dependent Schrodinger equation, we have IH bar times the time derivative acting on the wave function is equal to this particular operator acting on the wave function, an operator associated with the energy of the particle. So then we found this kind of reduced differential equation that has no time dependence, right? It's just a function of position, and it's an eigenvalue equation. So that differential, that operator acting on the wave function is some number times times the wave function, and the number is right now unknown, of course. But then in order to be able to satisfy that equation, we end up having like a certain set of numbers, as we'll see in several examples that we will do later in the course. So this equation is one of the most important equations of the course. Like if you think about atoms and molecules and even like solids, of course the equations can become more and more complicated if you have more particles. But there are generalizations of this to higher dimensions, to more particles, etc. And that really governs the allowed states of a system. So stationary states are basically the configurations that quantum systems take if they're just sitting somewhere. Okay, so the first example that's often discussed in finding solutions to this time-independent Schrodinger equation is something called the particle in a box. It's basically like an infinite potential well. So suppose this is x, this is the x-axis, here you have 0, here you have a. So basically consider a potential that is equal to 0 for x between 0 and a. So in this region it's 0. And then outside this region, for x larger than a or smaller than 0, it's infinity otherwise. And let's say we want to find the solutions to this equation for this particular potential. So our equation is, writing it explicitly, it's minus h bar squared over 2m, second derivative of the wave function with respect to position, plus v of x times the wave function. This is just now a function of position, right? That's the time-independent stationary states, is e times psi of x. Okay. And ultimately, we're interested in a wave function that's normalized, right? Because remember, psi x absolute value squared is the probability density, and the probability of the particle being somewhere is 1. So we want to have something like that. And notice that if you find the solution to this equation, right, suppose psi of x is a solution, you multiply it by any constant. So let me write that more explicitly. So suppose you have a solution like that. I multiply both sides of the equation by some constant. So then I can write alpha psi x plus v of x. Again, alpha is some constant, so I absorb it here, is e alpha psi x. So I didn't do anything. I just took that equation and multiplied both sides by alpha. And you see if psi x is a solution, alpha psi x is also a solution, right? So in order to fix like the coefficient in front, we want to find a normalized wave function so that this can be interpreted as a probability. All right. So now, if that's the case, right, we basically want this psi x to go to 0 at infinity, because its integral from minus infinity to infinity must be finite, so then we can divide it by some constant finite number and get that to be 1. If that integral is infinity, there's no constant we can divide it by to get it to be equal to 1. So like there are these constraints on kind of normalizable wave functions that they go to 0 at infinity. And in particular, if the potential is infinite, right? Suppose you have some range where the potential is infinite. Like, that's a huge thing. And if you have some finite energy and some finite wave function, I mean, on this side, you have a finite thing. This you can just neglect, right, compared to that. So the only way you can have a solution is that in regions where the potential is infinite, the wave function is 0 to kill it. Otherwise, this is the only infinite term in that equation and everything else is finite. So you can't have infinity equal to a finite object. So this really gives us a condition, because the wave function is because the potential is infinite outside this range from 0 to a, I must have psi of x is 0 for x smaller than 0 and x larger than a. So it's going to be something in between. Another kind of important consideration is that wave functions are continuous. Again, this has to do with wave function squared being a probability distribution, right? In order for it to just make sense for some region, you have some probability of being in that tiny region. If you talk about a tiny region located on X, like, you can't really talk about the probability if you have a jump in that probability, right? Because then it must be kind of independent of where exactly you put that interval around X. And if you move it a little bit this way or that way, less than the size of the interval, that probability shouldn't change. So that's also a requirement that these wave functions are continuous. There is no jump in the wave function. So given that, we basically can reduce the problem to this interval from 0 to a. So it becomes find psi of x for this interval between 0 and a, and then we have some boundary conditions. We know that psi of x equals 0 must be 0, because outside this region, it's inside the infinite potential, the wave function has to be 0. And then if it's continuous at the boundary at x equals 0, it must be 0. And also psi of x equals a must be 0. Okay, so we have these boundary conditions. And a simple equation. Now, in that region, the potential is 0, so our equation is minus h bar squared over 2m, second derivative of psi with respect to position, is just e times psi, right? The potential is 0 in this range. Again, we're talking about between 0 and a. So using some information about the wave function being continuous, about the wave function cannot be finite if the potential is infinite, so otherwise, you run into a problem with that. We reduced the general time-independent Schrodinger equation, which has like different components. There are three regions, right? Minus infinity to 0, 0 to a to infinity, to just an equation for the middle region. And this is a simple differential equation. The second derivative of a function of position is some number times that function of position. So that's something we can solve, and then we can make use of these boundary conditions to determine kind of the allowed values of energy, the allowed values of E, and then we can use the normalization condition to normalize it. So next time we will just continue this discussion of a particle in a box and try to solve the time-independent problem completely. Okay, that's a good place to stop for this lecture.